All right, so today's lesson will be all about waves and what they do when they get into a new medium. Okay, what kind of things about them change, all of that kind of stuff, right? That's what we're going to work on. Remember also, guys, that coming up here, okay, your pendulum labs were due at the start of class today, so hopefully you all submitted those. I know a bunch of you already had. Okay, that Galaxy Land assignment, remember, is June 12th, okay, that will be due. All right, make sure that you are working on that with your group mates, okay? And then June 13th will be the Unit 4 exam, and then we'll be reviewing after that, okay? So that's what's coming up here for us in the next little while. All right, so like we said, we're going to learn what happens when a wave encounters a boundary between two media. Now, what does a medium control about the wave? Yeah, exactly. It controls the speed. If the speed changes, what else changes? The wavelength. What never changes? Frequency. All right, good. Okay, so I'm going to have you just read this over here for a sec, and then we'll get back to it here in just a second. So, just a couple things here, guys. So obviously waves can travel through lots of materials, okay? And we talked about a little bit about that last week, how transverse waves tend to travel through less dense materials more easily than more dense materials. Longitudinal waves tend to travel through more dense materials more easily than less dense, right? So what we're going to look at here is what happens to those waves when they go from one medium to another, right? So if we're looking at light, okay, we know that light does this weird kind of bendy thing when it goes from one medium to another. Yes, yeah, okay, the medium is whatever it's traveling in. All right, so light does this weird kind of bendy thing when it goes into a new material. Like if it goes into water, it slows down. I'll actually show you here in just a second. It's gone into the medium at one speed, but it's coming out of the, or going through the medium at a different speed, okay? And so that changes the direction in which it travels as well as its wavelength and frequency. Not frequency, velocity.
Like going the same direction but slower.
I'm going to show you. Okay, that has to do with this diagram right here. If light or any wave comes into a boundary at an angle, part of the wave comes in or enters that medium before the rest of the wave. And now my smartboard's out of whack. The reason it bends and changes direction is because part of the wave enters the new medium before the rest. So this part of the wave is still traveling fast. This part of the wave has slowed down, okay? So it's like if I'm walking, down the hallway and I stick my arm out and I catch on like a door frame, right? That part of my body slows down. What does the rest of my body do? Yeah, and turns and pivots around it, right? It pulls me around because part of me is slowed down. Okay, that sort of makes sense? We've all, you just grab on something and you kind of spin around it. Well, that's really what's going on here, okay, is because part of the wave is slowing down before the rest. Once the rest of the wave gets in, then the whole wave is going in the same direction, but not the same direction that it was going before it slowed down. Okay, we call that refraction. Okay? It's the bending of a wave due to part of it slowing down before the rest of it. It's most easily seen with light. Okay? All right, so we got incident ray here. This is a much better diagram of than what I drew. Okay, it's coming in this way, okay, and then bending and going a bit slower. Okay, if it slows down, it bends towards this line we call the normal. If it's coming out of the glass, so if it was going this way, okay, then it would do what? Where's it going to go faster, glass or air? All right, and so instead of slowing down and bending towards the norm, it'll actually do this. It'll speed up and bend away because the waves that are getting out first, or the parts of the waves that are getting out first, will get longer and faster. Okay, so it bends the other direction. Yep. Well, it's not exactly the same. It depends on kind of how that medium is constructed. With these lenses, or these ones here, it was a rounded surface, right?
So for a diamond, does it bend light or is it just reflected?
It does both. Okay, here's the thing with that, okay, and that's a good question, is there's something called a critical angle, all right? And if I go beyond that critical angle, okay, so you can see here I got the light kind of coming through. I'll do it with the laser. Just there's going to come a point where I'm not going to get any light going through the prism. See how the light's not going through the prism anymore? Okay, that's what we call the critical angle. So there is an angle, okay, at which right? See how there's no light coming out? There's some light coming out, right? But if I increase the angle, none comes out. Okay, that's what they want to do with the diamond, is make sure that bottom angle is at the critical angle where light can't escape out the bottom. It'll always reflect. That's what makes it sparkle out the top, right? Okay. So, right, speed changes. Now, if we're looking at waves on a spring, okay, then it's a little simpler, right? But there are some rules for waves, one-dimensional waves traveling on a spring, okay? If we're moving from more dense to less dense, okay, then the wave is going to travel, no, if it's a transverse wave, it's going to travel faster in less dense material, okay? What's that? Slower in the more dense. Okay, so I've got this pulse here in the more dense material. Okay, when it hits the boundary between more dense and less dense, okay, it's going to reflect. Part of it is going to reflect, and part of it is going to travel into the new medium. Anytime there's a change in medium, some of the wave energy will be reflected. Okay, that's just always the case. Anytime there's a boundary, some of the wave energy gets reflected back. Okay, it's this reflected wave that can tell us about the relationship between the first medium and the second medium. If I've got something going from more dense to less dense, okay, the reflected wave will be upright. That is, it'll look the same as the wave that came in, but it'll come back the other way. The transmitted wave, that's the one that goes into the new medium, always looks like the original, but it could have slightly different properties. It could be, if it's going faster, and longer, right? Okay, faster and longer. Okay, everybody with me there? Yeah. Okay, so that's what we see here, right? This pulse here is fairly high. It's got a pretty decent amplitude, okay, but it's only that long. Transmitted wave is longer because it's going faster. Okay, part of it's sped up and ran away from the back of the wave. Okay, so it's stretched out. The opposite is true if I have waves going the other way. So they're going from the fast, less dense medium into the more dense medium. So when they hit the boundary here to the more dense medium, a fair amount of the wave energy gets reflected back. And it gets reflected back, and, well, not in just in the opposite direction, but also the opposite, yeah, amplitude or orientation, right? A crest becomes a trough. We call that inverted. Okay, it's an inverted reflection. This is an upright reflection. No, you'd still see it. Yeah. I mean, otherwise you wouldn't see a reflection. When light bounces off a mirror, it reflects back inverted, but you still see yourself. Yeah. Just because it's going into a more dense medium. That's just what waves do. When they hit a more dense medium, they reflect back inverted. It's more difficult to go into that medium. So more of the energy is reflected back. Okay? And we can see here that our transmitted wave is much shorter, and that means it's going slower. All right, this is exactly the kind of thing I might put on a multiple choice question. I'll show you a before, a during, and an after kind of a situation, like 3 pictures. Okay, here's the original setup, and a little while later you see this. What's the relationship between medium 1 and medium 2? Okay, which one is slower, which one is faster? Okay, that kind of thing, and you have to do that based on the shape and orientation of the waves. Okay, everybody follow there? All right, so I'm going to show you that now with the slinkies. Okay. Transverse waves. We can't see the longitudinal ones. It doesn't work the same, right? Okay, Angela, can you just flip those lights back on for me? I'm not going to use that really long one because it'll be too long. Oh, it's not really a slinky. It's just a spring. There we go. That's a short one. Okay, I will need somebody to hold the other end of this. Dave, you have experience, so you get hired. There we go, all the way to the filing cabinet. And we'll put them on the floor. Okay, so we got obviously two different media here. We've got a fairly tight coiled spring, and then we've got the slinky. All right, everybody with me on that? All right, so if I make a wave and send it towards David, okay, when it gets to the boundary between this spring and the slinky, some of it should be reflected, and some of it should get through. All right, so let's have a look at that. Okay, where did it travel faster? Yeah, definitely in the slinky. Okay, so, all right. When I got the reflected wave back, it was upright. It's hard to see because it's very small, okay? But some of it came back upright. All right, so we'll try that again here. Okay, so little of the wave energy reflects back when we're going this direction, okay, that you hardly even see it because it's going from the easy medium to the hard medium. So now I'll have David make one the other way. Okay, try it again, make a big one. All right, did you see that the reflected wave was the other way? Okay, try it again, David. Okay, so he got a reflected wave off the boundary that was inverted and going back to him. Okay, so going this way into the slower medium resulted in an inversion, okay, of that reflected wave. Okay, all right, good, thanks, David. Whoa. Yes, I have, and it's bad because it takes you forever to get the kink out. Just put that on the desk there with the other stuff. Thanks, David. It's a spring, a wondrous thing. Everyone knows it's slinky. What? What do you mean? How come it doesn't just fall over? Yeah, you can get it to walk down the stairs. Yeah, it's just because all the mass is connected, right? The front part of it goes down and pulls the rest of it over, but then it's got momentum, so the momentum carries it over to the next, over the edge of the next stair. Okay. So everyone following how that works. So this is something you're just going to have to memorize, okay? But you're going to have to know that when we go from more dense to less dense, okay, we're going to get a reflected wave that is upright, okay? And some books will use the term erect. I don't, because it gets exactly that reaction. People giggle, okay? Anyway, upright, that's what I will use, okay? If it is going from a less dense to a more dense medium where it's going to slow down and have a shorter wavelength, then more of the wave will be reflected back inverted, okay? We just have to remember that. It's just something we have to memorize, okay? All right, so rarely is this all or none, okay? There's partial reflection always at a boundary. Some of the wave energy is not going to get through when we change media, right? That reflected wave tells us a lot about that stuff. Okay? Now, what does that mean for amplitude then in general? If I'm getting some reflected wave energy going back, the transmitted wave is always going to have less energy, right? It may still end up with a higher amplitude if it gets really squished, but in general, the wave is going to have less energy because it's losing some of it at the boundary. Some of it is just being reflected back, okay? So it'll have less energy that way. Right, so the determining factor, okay, of how much energy is reflected or transmitted is how similar the media are. Okay, if they're very different, like light going from air to diamond, there's a lot of reflection. If they're very, very similar, like we're talking going from one type of glass to another type of glass, okay, you're going to see very little reflection because the wave doesn't change very much. It's not really changing the medium significantly, so you don't see a lot of difference. Okay, everybody all right with that? Right, so the more reflected wave energy we get, the more dissimilar the media are. All right, so reflection. One of the behaviors of waves that we're going to talk about is reflection. So that's anytime wave energy reflects from a more dense medium, okay, the reflected wave will be inverted, okay, reflection off a less dense medium, okay, it'll be upright, okay, these used to move, but for some reason now they don't, okay, and they were going to show that, but That's just the thing we need to know about reflection. The other thing we need to know about reflection is that whatever angle a wave comes in at, it goes off at exactly the same angle, right? If you've ever tried to like blind somebody, you know, by using something reflective, like maybe the face of your watch catching some sunlight and then trying to get the little dot, or you're doing that with your cat and they're chasing it or whatever, okay? The way you get that thing to go where you want it is getting the angle right. The angle of the incoming rays is always going to be the same as the outgoing rays. Okay, that's called the law of reflection. Okay, it's always true, even off a curved surface. Okay, it's going to be true. So just that's the law of reflection. The incident angle is the same as the reflected angle always. And this comes in handy because it's not just true for waves, it's also true for particles. Okay? So if you throw something and it hits something, it'll bounce off at the same angle it came in at. Keep that in mind if you throw it straight at something, because it'll come straight back unless you're spinning it. Okay, if it has a fair amount of spin, then that could impart a change in angle, but if it's just hitting it, it will come off at exactly the same angle it came in at, which is especially useful if you're playing pool and you're trying to hit a bank shot. Okay, particles behave just like waves. And this is the odd thing, it's just like looking in a mirror, except it's for a ball instead of doing your hair, right? So if I want to make this shot happen, so this ball is here and I want to hit it with the cue ball, obviously I can't go this way because you can't hit the 8-ball, okay? Can't use the 8-ball in a combination. So I would aim for some point on the bumper, okay, and hope that my cue ball will come off of that and hit the ball I want it to hit. The trick is knowing where on the bumper I have to hit. Okay, how many people know how to do this without guessing? Okay, here's how you do it. The bumper is a mirror. It's going to reflect anything that hits it. Okay, any ball that hits it is going to reflect off. And so just like when you stand in front of a mirror, your reflection is how far behind it? The same distance you are in front of it. Okay, next time you look in the mirror, now you're going to think about that. Oh, I'm that far. Your reflection is always the same distance behind me. If you take a step back, what does your reflection do? It takes a step back because it's you, and it's going to be the same distance behind the mirror as you are in front of it all the time. So what you do is you essentially kind of measure how far the ball is in front of the bumper, and then you go that far behind it. Okay? And then from there, you can find the mark on the bumper. So when I was in university, you know, we would go and play pool at the bar sometimes at night, and this is how we would always make sure we would hit the bank shots. Some people didn't like it because they thought it was dirty pool, and we're like, hey, we can't help that we're smarter than you and know how to do physics. Like, physics is awesome, and you're going to pay for our pool game because of it. Okay, so what we would do is we would have your partner stand this far behind the bumper and hold the cue right in front of him. And then I would stand over here and sight to the cue, and I would know right where that line hit the bumper. That was the mark I had to hit the ball to. Okay? And then I can hit a bank shot every single time. Well, till later on in the night when for some reason I wasn't hitting things as well. But yeah, okay, sometimes that would happen. Yeah, you just, something about your, you know, shot plane just deteriorates throughout the night for some reason. Yeah. Okay. So yeah, that's how you can hit a bank shot each and every time. Imagine that this is a mirror, okay, and you go exactly the same distance behind it, and then sight along that line to the bumper. You'll hit the bank shot every single time. Okay, so now you know. Now you can be better at pool than other people. That's not going to work until you're good enough at pool to actually hit the ball to that spot. Okay, without spinning it significantly. If you hit it like kind of sideways and it spins, it'll spin off the bumper and it won't work. Okay. All right, so I'm going to show you a quick video here on like reflection and waves. Okay, this is actually a picture from it, but okay, so that's reflection. Now, the transmitted waves, we have to remember, the transmitted waves are always going to be upright. If it came in as a crest, it's going to go through into the next medium as a crest. That never changes. The transmitted wave is always the same as the incoming wave or the incident wave. Okay, we also remember that the frequency remains the same. Nothing can change that. Speed and wavelength will change and keep it the same. Okay, velocity is going to change, wavelength is going to change, amplitude can also change. All right, we are going to lose some energy due to reflection at the boundary, so our amplitude is bound to change. Even if we lose very little energy, okay, we know that the wave is probably going to either lengthen or shorten, and that's going to make the amplitude look different regardless of what happens elsewhere. Okay, so that's the stuff to remember about the transmitted wave. Okay, frequency will be the same, orientation will be the same, it'll be upright. Okay, and then obviously our wavelength and velocity will change. Okay, we often will represent waves with a wave ray, just an arrow to represent a series of waves, because it's easier to draw that than all these lines. Okay, so we just draw a wave ray that represents a whole bunch of incoming waves because it's just easier to do it that way. Okay, it is always drawn 90 degrees to the wave fronts. Basically, it shows us which way the waves are traveling. All right, and then we have this normal line that we were talking about before. The normal line is just an imaginary line that's a reference so that we can compare the angles of the incoming waves or the incident waves and the angles of the outgoing waves. All right, everybody with me on that? Okay, so that's all it's there for. It's not a real line, it's just one that we use that's imaginary. It's always 90 degrees to the boundary. Okay, so here's the boundary, here's our normal line. So I might have, waves coming in like this. Okay, so they would look, those would be my incoming waves, but my outgoing waves would look like this. All right, so did they speed up or slow down? They slowed down. Okay, they slowed down because they bent towards the normal. All right, so if I continued to draw these, okay, right, you can see that their wavelengths got shorter, their direction changed to this, okay, and that's because they slowed down. All right, you'll learn a lot more about this in Physics 30 when you take Snell's law. Okay, Snell's law deals with the relative speed and angle and wavelength of waves when they enter a new medium obliquely, like this, so at an angle other than straight on.
Does the mirror just work because it's so much denser in the air reflects so much of it?
No, anything reflects stuff back. A mirror is just like polished enough, right? Just like the surface of water is flat enough, okay, that we can see our reflection in it. Okay, so it's, yeah, any polished surface is going to allow you to see a perfect reflection because the reflection is perfectly straight back. Okay, I can't see myself in the wall because the wall is painted with flakes that diffuse the light everywhere, right? If that was really glossy, then I might be able to see the glare of the lights in the wall, or even if I was, if it was really glossy, I might even be able to see kind of a shape of myself in it. Okay, because if it's glossy, it's got a sheen that's flatter than flat paint. Right, which is odd because we call it flat, but it's not, it's glossy. Yeah. Okay, everyone with me on that one? All right, then angle of incidence and angle of reflection. So the angle of incidence always means coming in. Okay, reflection is outgoing, refraction outgoing. Okay, so incidence always means coming in. Anytime we have reflection, the angle of incidence, which is this angle here, is equal to the angle of reflection. Okay, always, doesn't matter what the surface is. Okay, it's always going to be true. Something makes a diffuse reflection of light like the walls because the surface is very rough. Okay, and that even though everything is reflecting off the angle it comes in at, the angles are always different because the surface is not perfect. Okay, and when we're talking about light, the surface has to be pretty perfect in order for that to work. Okay, because light has a really, really small wavelength, right? And so when it reflects off, okay, it doesn't work. Sound reflects off these walls very easily because sound has a much longer wavelength than light does. All right, refraction's our next one. So I'm going to show you the videos here on refraction. Okay, they show you some pretty good examples of light bending and changing speed. Okay, here's another diagram of it. We can see that out here, the waves are quite long, but in this medium, the waves are shorter. Okay, if we had a normal line, okay, that would be it, 90 degrees to the boundary, right? So we can see that these were the incoming or incident waves. These are the refracted waves. They bent towards the normal, okay? So they were slowing down. If we're looking at that the opposite way, so let's say these were the incoming waves, okay? They go off at this angle, but the outgoing waves bend away from the normal, so they've sped up, okay? All right, refraction. Okay, now this, they were talking about this. If anyone's ever done spearfishing, okay, that whole thing with the, you know, the bent stick and the gamuts going down, okay, that's like this. Okay, if you have ever done spearfishing, okay, the fish always looks closer to the surface than it really is. So you're standing there and you're seeing a fish a little ways away, you aim for where the fish is, you miss. Okay, because that's not where it is. Okay, if they're closer to you, it's less of a problem because you're looking straight down on them. But if they're kind of that distance away, that's where it's really disconcerting because you have to aim closer to your feet if you're actually going to get the fish with the spear. Okay, so there's a lot of refraction that plays into that, okay, that you have to be mindful of. All right, and that's what we were talking about here before, that it bends towards the normal if it's going into a slower medium, bends away from the normal if it's going into a faster medium. That is something you should probably make note of, okay? That it bends towards the normal if it's going from fast to slow. It bends away from the normal if it's going from slow to fast. Okay, and like this is kind of what they were showing us with that block in the ripple tank. Okay, we saw that the waves were fairly close together, okay, or sorry, fairly far apart out here, but once they got to the block, we could see the effects of that change in depth on the waves. They got shorter versus the ones that were longer on the outside, okay, and we can also see that to an extent, okay, if we're talking about waves coming into a shallow area versus waves staying in deeper water out here. Okay, we can see that here in the shallow area, okay, where this peninsula is, okay, that the waves are getting slowed down a little bit. They're getting turned. It actually, here it kind of looks like they're wider, but it's just because the white stuff is crashing here. Okay, but we can see that out here, the waves are a lot longer out here, and that's because this part of the waves in this area here is in the very shallow water. They're getting slowed down, and it's causing the wave to fan out and change direction so that it comes into that cove. All right, that's just the process of refraction, okay, that's causing that slowdown of part of the wave versus the rest of it. Okay. All right, this one's not in your notes. I need you to copy this one down because I forgot to put it in your notes. Diffraction is the final behavior of waves that we need to talk about. So I'll let you copy down just that sentence, and then we'll talk about what diffraction is. You may want to add a couple of things as we go along. So just give you a minute to get that sentence copied. Okay, so diffraction is a behavior that only waves exhibit. Particles will not diffract. Okay? Diffraction has to do with when a wave encounters either a narrow opening or an obstacle. Okay, and this was actually the big point of contention between most scientists when they were kind of studying light early on. Okay, during the study of physics, they found, or a lot of them thought, that light had to be a particle. Okay? The bulk of scientists thought light was a particle because it showed all the behaviors of a particle and that it did not diffract. It didn't do this. Okay? What they didn't realize, of course, was that light travels extraordinarily fast and has an incredibly small wavelength. Okay? The faster a wave travels and the shorter its wavelength, the less it diffracts. Okay? Those two things, higher speed and shorter wavelength, mean less diffraction. Okay, the longer and slower a wave is, the more it diffracts. The reason for that is the slower and longer it is, the more it's in contact with the opening or the obstacle. So the obstacle or opening has more chance to alter and interact with the wave. Because light's so fast, it's through an obstacle or around it, okay, or through an opening so fast that it barely has any time to do anything. Okay, and so scientists would look at things like if the lights were off in here and the door was open, a beam of light would come through the door. Okay, just the beam. If light was a wave, then it should fan out. Okay, that's what diffraction is. And we see that here in the diagram. Waves come to this narrow opening and they go through the narrow opening and they diffract. They become curved because the edges of the wave interact with the opening and they get slowed down and it bends the wave. Everybody with me on that? Okay, particles don't do that. Okay, if I had this room like, well, just like really bright and this area really dark, okay, all people would see would be a beam of light that got through the gap, right? People saw that and went, light is a particle, because if it was a wave, it should do this, and it doesn't. They also had this great set of evidence that followed everyone everywhere. Your shadow, yeah. If light was a wave, why do you have a shadow? It should just diffract around you, okay? Just like the waves do with this person and this obstacle here, okay? If I sit right behind this pole, I can still hear this, okay? The sound waves will diffract around it. They'll be altered slightly, but I'll still hear sound, okay? It's not like it blocks the sound completely, but it would sure block light, right? There'd be a shadow behind that pole, right? So they had a lot of evidence, simple, kind of irrefutable evidence that light was clearly a particle. It didn't do this, okay? It took a really brilliant scientist, okay, named Thomas Huygens, okay, who developed this double slit experiment to show that light actually was a wave. Okay? He had this idea that light, if it came from two places, would behave like sound that came from two places. Do you remember us doing the two speaker questions last week? Okay. He said he could make light do the same thing. Right? And people laughed at him because clearly light doesn't do that. If I put two lights at the front of the classroom, I don't get striped light on the floor, okay, like I do with sound. I don't get loud spots and quiet spots, okay? I get light everywhere, okay? What people, again, didn't realize is that light has such a small wavelength that we can't see these areas of light and dark. They're there, but they're so small that we can't see them, okay? Everyone kind of with me there? Okay, so this is what, sorry, not Huygens. This is Young. Sorry, Thomas Young's, not Huygens. This is what he did. Okay, he set up an experiment where he had a light source back here, and he had a very, very narrow slit. Okay, like we're talking like 10 to the minus something meters, like really, really small. Okay, and then he had another barrier that had two slits in it, and he said, I'm going to turn this light on, and I'm going to see a pattern of light and dark on this screen that I'm going to set a few meters away. Okay, and most people looked at him and went, you have been in the sun too long. Okay, like you turn a light on, you're going to get a beam of light coming through this first slit, it's going to hit right here, and your experiment will be over. You're an idiot. Okay, he was laughed out of like universities everywhere because people said, this is not going to work. Light's a particle. You're just being stupid. Okay. Well, he got the last laugh. Light's a wave. Light diffracts. And that's exactly what happened here. Okay. He got the light to diffract through this because the opening was small enough that it could affect the incredibly small wavelength that light waves have. Right. So they went through this, and then these two openings here acted like two speakers. Two separate sources of waves, except they were for light instead of sound, right? So he got waves diffracting out of this one, okay? And those shouldn't have crossed. Those shouldn't have crossed there, okay? And waves diffracting out of this one, okay? On his screen, he got light spots and he got dark spots. Okay, light spots, light spot, okay? This would be a dark spot, okay, on the screen, okay, where the light interacted. Now I had to put the screen a fair ways away. These two things had to be very close to each other, like almost on top of each other, so that the small wavelength of light could actually be demonstrated, right? This was Young's double slit experiment, and it proved unequivocally that light was a wave. Even guys like Newton went when it happened, okay? Because there was really no argument for light's a particle, guys. Okay, there couldn't be. When light did this, it was clear that it had to be a wave. Particles would never have gotten through the second set of openings, okay, because they would have just hit the back of that screen. Okay. All right, so that's diffraction. So diffraction, like we said, is the bending around or through a narrow opening. So the wider the opening, the less diffraction there's going to be. Okay. The slower and longer the waves, the more diffraction there'll be. The faster and shorter the waves, the less they will diffract. Okay, but they will diffract. Okay, and they'll diffract either around an object or through a narrow opening. Okay, we can kind of see that here in this diagram here. We got fairly straight waves, but as they encounter these rocks, right, they get bent. Okay, they go through that opening, they get bent into circular shapes. They even get bent as they go around. Okay, this kind of rocky outcrop here. Right, we can even see that pattern of kind of constructive and destructive interference as they go. Okay, so we need to know those behaviors of waves. Okay, easy multiple choice question on this exam could be, which of the following diagrams is showing refraction? Which of the following diagrams is showing reflection, et cetera, et cetera. Okay, you have to identify it from these. Okay. All right. Okay, so I've got some questions I want you guys to work on here. They're fairly easy. They're just, waves going to a boundary. What are they going to look like after? Here's the before picture. What's the after picture look like? That kind of stuff. Okay, I'll put that up on the board here in just a second. Okay, question? Yes? No? Okay, so on our first one, we're supposed to draw a trough approaching a fixed end, and then a second sketch showing that wave after it is reflected off the fixed end. All right, so a trough looks like this, right? So we've got a trough, and it's approaching what we call a fixed end. That means if it's a spring, somebody's holding the other end, or it's tied to a wall or something. It can't move. Whatever wave I make, the next medium it goes into is the wall. Okay, and is the wall pretty dense?
Yes.
Like it's almost, compared to the spring, almost infinitely dense. So really no wave energy is going into the wall, right? Because if I'm making a trough and I've got this trough traveling through a spring and it hits the wall, I don't see the wall ripple. Okay, basically none of the wave energy goes into the wall. It just reflects off. All right, so I've got this wave and it's going this direction towards the wall. All right, a little while later, what am I going to see? Right, I'm going to see an inverted wave going back. Okay, it came in as a trough. It's going to reflect off of a more dense medium, so it's going to invert, okay, become a crest, and go back. And it's going to have the same wavelength as the incoming wave because it hasn't changed media, right? It just bounced off.
It wouldn't even be slightly smaller?
Well, the amplitude could be slightly smaller, but the wavelength isn't going to change. It's still in the same medium it was before. Okay, and even the amplitude is not really going to change because this is a fixed end. It's not taking any of the energy, right? It's just bouncing it all back. Okay, that sort of makes sense to everybody? All right, so that's another term. So I think I forgot to mention what fixed end meant. Okay, fixed end just means the medium is tied to something and it can't go any further than that. It would be something I would look for. If you drew them significantly different, then I would go, oh, okay, that seems to show me that they don't understand what's going on. So as long as they're close, like mine aren't exact, they're close, right? Like I wouldn't look twice at that. I would say, oh yeah, okay. But if my second diagram looked like this instead, I would go, ooh, do they understand that most of the wave energy should have come back? That diagram doesn't say that. Yeah. All right. How many people have done number 2? Okay, let's have a look at number 2 then as well. Okay, so waves before, during, and after complete destructive interference. So if they're going to completely interfere with each other destructively, they have to be opposite and equal. Right, their amplitude has to be the same. So I'm going to have an upright wave and a downward wave. Those are about the same. They're supposed to be anyway. Okay, and they're traveling towards each other. That would be the before picture. Okay, the during picture would look like this, because they're going to completely interfere with each other. Sometimes we do this. We kind of show that's where they are, but they've completely destroyed each other. Okay, then the after picture. Okay, again, I'm not measuring and making sure my amplitudes are exactly the same as they were in the first, but they're close enough that, okay, I know you're not thinking the amplitude has changed. Okay, that would be the after picture. They go on completely unaffected in the same direction they were traveling before. Okay, all right. How many people have done number 3? Okay, so let's have a look at 3 as well here. Okay, so where the wave is moving, is the wave moving from a faster medium into a slower one or the other way around? All right, so I've got this upright pulse that hits the boundary. A little while later, I have a reflected pulse that's inverted, and I have a much smaller pulse, not only smaller in amplitude, but also shorter, moving into the next medium. So is that next medium more or less dense than the first? More dense. The wave slowed down and got shorter. That's what I would be looking for as an answer. Okay, if this was like a written response question, okay, I would want to have you say it's more dense, and here are the 2 reasons why. There's an inverted reflection, and the transmitted wave is shorter and smaller. If it's shorter, it has a lower velocity. The height of it has to do with most of the energy being reflected off the boundary. Yeah? Okay, keep going then, guys.